This is question 14. The beginning part of the question is on the other side of the paper, but basically you've got two different circuits that have been set up. We have an unknown voltage here. In actual fact, we call this the EMF, which is the total energy per coulomb that can be supplied by a cell. Now, what often happens with a cell is that within the cell itself there is some resistance which uses up some of that energy per coulomb. And so when you measure the voltage, when you do a voltage reading when there is no current flowing, it will be higher than when there is a current flowing, and that's called the EMF. I will discuss that more in class. But in so doing it, you use this formula over here where E is the EMF. That's the actual reading. This is the reading, the voltmeter reading, when no external current is flowing. Current flowing. So we're going to, what we are wanting to work out with this is to work out the internal resistance of the cell. This is actually the resistance within the cell. Okay, so we're also going to use this formula over here, and we know that that will be the same for both of these. That will be the same for both, but I can put in my values for this. So for the top circuit over here, don't worry about this, this is a mistake. For the top circuit, you're going to have your I, which is 2.2 milliamps, so it's 2.2 times 10 to the negative 3 amps, and it's times R, that's your resistance within your circuit, so that's 100, plus the R, which is your internal resistance, that's your internal resistance there, and that equals, I'll just keep going across there, for the other one, for this circuit, it's also got the same EMF, so this is the same, so I can equate them, and that is going to be 1.5 times 10 to the negative 3, and here we have a external resistance of 150 plus that same R. So we're going to equate them. Now here I've got this 10 to the minus 3 in both. I can just multiply it by 1,000 through and I can get rid of that. I multiply this through, I'm going to get 220 plus 2.2R is equal to 1.5 times 150 is 225 plus 1.5R. And then I can just take the R over to that side there and the number over to that side. I'm going to get 2.2R minus 1.5R is equal to 225 minus 220, and I get 0.7R is equal to 5, and when I divide 5 by 0.7 I get about 7.1 ohms. So this over here would be the correct answer for that. Moving on to question 17. Determine the equivalent resistance when 12, 6 and 4 ohms are placed in series and in parallel. So in series it's pretty straightforward, we just use that formula over there. So your R total would equal 12 plus 6 plus 4, so that's 22 ohms. No problem with that. In parallel, it's a little bit more complicated, in that we're going to use this formula over here, that we're going to get 1 over RT is equal to 1 over 12 plus 1 over 6 plus 1 over 4, and then we can do this by calculator, or we can just do this by using our fractions. We can use 24 as the lowest common denominator here, so it's going to be 2 plus 4 plus 6, so 1 over RT. So this is going to be 12 over 24 1 over RT. So we invert both sides, and we're going to get 24 divided by 12. We're going to get 2 ohms. So the equivalent resistance for this, for the parallel, would actually be 2 ohms. And so when we do this, when we put these in parallel, we see that we are lowering the resistance. Question 18. Calculate the work done in moving 12 microcoulombs for a potential difference of 240 volts. We know that V is equal to W over Q. So we're going to get W is equal to V times Q. And so we will get 240 times 12. And remember, this is micro, so it's 10 to the negative 6. So we would need to work that out, and we would get our answer there. Okay, that shouldn't be a problem, and that would be in joules. Question 19. We have the following circuit. It says determine the total resistance of the circuit. Now, in doing this, I've got these two that are in series, so that's fine. I'll just be able to add those two. But I firstly need to find the equivalent resistance of the parallel section. So I'll do that first. So I'm going to, for that part, for the parallel, 1 over Rp will equal 1 over 6 plus 1 over 4. So 1 over Rp, it will be, I'll do it over 12. It's going to be 2 plus 3. So I'm going to get 5 over 12 is equal to 1 over Rp. Don't forget you need to invert both sides. So Rp is equal to 12 over 5. So it's equal to 2.4 ohms. So I could effectively replace that 6 and that 4 by an equivalent resistor here, there, of 2.4 ohms, and that would give me the equivalent resistance. So my total resistance, therefore my R total, would just be the addition of these because they are now in series. So 2 plus 2.4 plus 20. So I'm going to get a total of 24.4. 24.4 ohms. Calculate the current flowing through the 2 ohm resistor. Now the 2 ohm resistor is going to have the total current flowing through it because it will go through there and it will split up here, but through the 2 ohms. So to work out the total current, we need the total voltage and we need the total resistance. So let me just get rid of some of this writing here. So I'll use this formula over here. I is equal to obviously V over R. The total voltage is 12.2, and I worked out the total resistance was 24.4, which is double that, so we can see that this would be 0.5 amps that would go through. So we would have our total current would be 0.5 amps. Deduce that the potential difference across the 20 ohm resistor. To do that, we would know that we have a current here of 0.5 amps. So my voltage is equal to I times R would equal to 20 times by 0.5 would give me 10 volts. So across the 20 ohm resistor, we would have 10 volts across it. Determine the potential difference across the 6 ohm resistor. Now, with this, there's different ways that we can work this out. We can look at it from a point of view of seeing what is the potential difference across the 2 ohm resistor. So I can say that's going to be 2 times 0.5, so you're going to get 1 volt over there, and we know that there's 10 volts there, and so here we've got a 12.2, so therefore the difference would be 1.2 would be across the parallel. So this would be 1.2 volts across there. That would be one way of doing it. There's other ways of doing it that we could use. We also know that we have here an effective resistance across here. We could use that effective resistance to work it out and determine the current through the 4 ohm resistor. Now, because we know that the voltage across each one of these is 1.2 volts, we can work out the current through each one. So in this case over here, your I is equal to V over R. So because it's 1.2 and it's 4 ohms, we would get 0.3 amps going through that. If I divide 1.2 through the 6 ohm, this would be through the 4 ohm. They don't ask me to work this out, but I can work it out. Through the 6 ohm, it would be 1.2 divided by 6, and that would be 0.2 amps. And as you can see, the 0.3 plus the 0.2, when you add them together, you're getting your 0.5 amps, which is your total current through your circuit. Question 20. A photoelectric cell draws a current of 0.12 amps when driving a small load of resistance 2 ohms. If an EMF of the cell is 0.8 volts, determine the internal resistance under these conditions. So we're going to be using this formula over here. We have got our EMF is equal to 0.8 is equal to our current is equal to 0.12. We've got an external load of 2 ohms, and we want to find our R. So it's just a matter of solving that equation. So we're going to get 0.8 is equal to 0.24 plus R, and times 0. Obviously that R is also times 0.12, and then I solve that for R. That shouldn't be any problem for you.